Welcome once again to Giants of Science. This week, Ernest Rutherford. He was born on August 30th, 1871 in Nelson, New Zealand. After early education in government schools, young Ernest entered Nelson Collegiate School at 16, where he won a junior scholarship to Canterbury College, Christchurch. He received an MA with double first in mathematics and physical science. 1894 saw Rutherford awarded an 1851 exhibition scholarship, taking him to Trinity College, Cambridge, as a research student under J.J. Thomson. In 1898, he went to Canada as a professor of physics at McGill University, Montreal. Rutherford's great talent was devising experiments so cutting-edge he had to design the apparatus himself. Einstein described him as a second Newton, changing our understanding of the nature of matter. He pioneered working with large teams of men and women chosen for their talents, not their backgrounds, sharing ideas and conclusions over afternoon tea.
Knowledge. It can change the way we look at the world. Knowledge can change our reality. From flat Earth to spherical planet, from the center of the universe to a tiny world orbiting a star on the edge of a galaxy. But how is that knowledge gained? Well, sometimes by accident, sometimes by design. But how do you solve a problem you've never come across before? Imagination, experimentation, invent something and then see if you can prove one way or the other if it's correct. As you probably know, I've had more than a passing acquaintance with the atom. I've studied its structure and behaviour under various circumstances. So if we look at the atom in cross-section, we'll start with a circle and at the centre, a dark, denser dot. Surrounding that, flying around, are lots of little tiny dots. Now, the blob at the centre is the nucleus. The nucleus is made up of two different types of particle. One is a proton. That's got a positive charge. The other is a neutron, and that has no charge, it's neutral. Flying around the outside are what we call electrons, and they are a negative charged particle. The number of protons, neutrons and electrons varies with different types of atoms. Now that structure, which doesn't cause much of a stir here today, was once a great and tantalizing mystery. Ancient Greek and Indian philosophers theorized that all matter was made up of tiny, indestructible particles, or atoms, the smallest things in their universe. The very name means indivisible. For millennia, it was just a theory, but bit by bit, the truth was revealed.
John Dalton identified atoms of different elements by calculating their weight, proposing that no two elements have atoms of the same weight.
These tangerines are all the same size and weight, or more or less. So let's say they're oxygen atoms. These potatoes are all the same, more or less, so let's call them hydrogen atoms. No two elements have atoms of the same weight. Dalton had turned a theory into a science, but still the structure remained a mystery. Now J.J. Thomson, under whom I was a research student at Cambridge University, put forward an idea that the atom was rather like a plum pudding. Well, rather like this one in fact. A number of negatively charged electrons, or as he first termed them, corpuscles, floating in a positively charged soup or pudding. Now in 1909, I devised an experiment to test this theory. But I'm getting a little ahead of myself. First of all, I need to introduce you to the alpha particle. Radiation, as coined by Marie Curie, had long been recognised but not understood. It seems that some atoms, or isotopes, are naturally unstable, rather like myself these days. Like uranium or polonium, they naturally emit radiation. But what's going on? Now the proton, which has a positive charge, and the neutron, which is a neutrally charged particle, are bound together with a powerful force known as the strong or nuclear force. Now sometimes this partnership is unstable, and what I found to be particles of different types break free. People like their own space. This person has their own personal space. How does that feel? But what if you have to share that space? Not so good. And the more people you share it with, the more repellent they become to each other. Until... If you push two magnets together with the same polarities facing each other, they are of course repelled, and it takes quite a force to hold them close together. This arrangement relies on that fact so that these two magnets can be suspended. The protons in a nucleus are all positively charged, naturally repelling each other. They're only held together with this great force, the nuclear force. But if the nucleus of the isotope or atom contains so many protons, they'll overcome this nuclear force and particles are emitted from the nucleus. This is known as decay or radiation.
The loss of protons and neutrons actually changes the chemical makeup of the isotope, transmuting one element into another. Alchemy, if you like. An element like uranium can transmute into lead. Lead could transmute into gold, although the cost would far exceed its value.
I identified two types of radiation being emitted from radioactive elements. The first I called alpha. The second was beta. Later on, a third was identified, which I called gamma. So, alpha particles are made up of two protons and two neutrons, which coincidentally are the same number of both that make up the helium atom nucleus. So, alpha particles are helium atom nuclei emitted from a radioactive element during nuclear decay. As I said earlier, the structure of the atom at that time could only be guessed at. So in order to probe the structure, I suggested to Ernest Marsden, who was a physics undergraduate at Manchester at the time, that he set up various strips of metal such as aluminium, iron and lead, but most famously, gold foil, only a few hundred atoms thick, and fire a beam of alpha particles at it to probe the structure. Given Thomson's idea of the plum pudding, what we expected was that the alpha particles would pass straight through the foil with barely any deflection at all, highlighted by tiny flashes of light upon a zinc sulfide-coated screen placed all around the foil and the beam emitter, which for the most part is what they did. However, about 1 in 20,000 were deflected through angles of 90 degrees or more. Some even bounced back. It was an astonishing result, as if you'd fired a 15-inch shell into a piece of tissue and it came back to hit you. There were one or two other things going on in 1909. Manchester United won the FA Cup for the first time, Ernest Shackleton discovered the magnetic South Pole, and Geronimo, or Goyakla, Chiricahua Apache, died at the age of 79. All quite fascinating, I'm sure, but for myself and my colleagues, compared to what we witnessed that day, everything else paled into insignificance. But how to interpret the results? Now, it's very important when faced with new data to keep an open mind. For example, if 3 people book 3 rooms for £10 each, the total amount paid would be £30. But if a bellboy is sent back with a refund of £5 to be split between those 3 people, but only £3 arrives, the miscreant bellboy keeping 2 for himself, you would amend what they've paid to £9 each. If 3 9s come to 27, that plus the 2 that the bellboy kept comes to 29. The facts can't have been interpreted correctly. If we start with the initial amount, take off the 5 that was refunded, that leaves £25. The bellboy keeps 2, that's £27, and 3 were refunded, that's £30. Having someone cross-check your work is also a very good idea. The deflection of the alpha particles must have been due to a dense mass, indeed the majority of the mass of the atom focused at the center of the structure, dense enough to deflect the alpha particles, the nucleus of the atom. The majority of the rest of the atom must be empty space, inhabited by the orbiting electrons. In fact, if this coconut, which is approximately 10 centimeters in diameter, were the nucleus of an atom, the outer circumference of the electron cloud would reach Manchester University Museum. And there would be nothing in between here and there except a few blue bottles buzzing around. So how has all this changed the world that we live in? Well, those early experiments and discoveries were the catalyst for a whole generation of Nobel Prize-winning physicists with whom I've had the privilege of working. James Chadwick, for example, discovered the neutron. John Cockcroft and Ernest Walton achieved atomic decay, or split the atom, as it was somewhat inaccurately termed, for the first time using completely artificial means. This proving for the first time Einstein's formula E equals mc squared, or mass you start with minus the mass you finish with equals energy created. The nuclear age had arrived.
These developments led to Britain's involvement in CERN and ultimately the building of the Large Hadron Collider and its examination of the very origins of the universe. Nuclear energy, of course, is one huge benefit of this age of particle physics, although some would argue that the dangers outweigh the benefits. And of course, the elephant in the room is the atomic bomb. Impacting perhaps to a greater extent is the wobbly dot. Few technical advances in history have more profoundly affected the global economy and social interactions than the web. This, in turn, has given birth to the grid, allowing physicists to manage and process unprecedented amounts of data across the globe. We have radiotherapy techniques in the treatment of cancer, biomedicine benefits, and diagnostics instrumentation. Accurate dating of the Earth through radiometric dating using the half-life of decaying elements. Over a period of time, half the material of a radioactive sample decays. Over the following same period of time, half of what was left decays, and so on, following a predictable rate of decay. The list goes on and on and on and on and on and on. And that brings us to the end of this current series of Giants of Science.